everybody. So we've spoken a lot about buffers and tried some problems in class, and we're going to continue to do that. But I wanted to talk to you a little bit about buffer capacity, buffer range, how to prepare a buffer. And so we've also discussed this in class a little bit, but just to summarize, when you make a buffer more concentrated, you have more moles of the acid and the base in the buffer. And so when you try to, or when the buffer is disturbed, adding H3O plus or OH minus, the buffer will have more moles to react. The more concentrated the buffer is, the less change you're going to get in this ratio of A minus to HA. And so when we either increase the volume of the buffer or we add more moles by increasing the concentration, we're going to get a better buffer range. The other thing is that a buffer is usually good between a range of, or a ratio where the base to acid or acid to base is 10 to 1. So that's going to be our range. So we could increase the base compared to the acid about 10 to 1 before the buffer starts to fall apart. And you're going to see that in some of the problems that we do with titration. So far, we sort of have done some sort of fun problems where we have, an acid and base buffer, and then we add a strong acid or strong base, and we see that the pH changes very little. When we do a titration, and you'll see that coming up, what's going to happen is the buffer is going to completely break down as we keep adding more and more acid or base. So we're going to talk a lot about acid-base titration curves, and I keep sort of alluding to the fact that you've done a little bit of titration last year, and you did MAVA equals MBVB, and you have an idea about that. But we didn't really get into things like titration curves or why indicators work, and those become really important for us. So you've always known, okay, well, I can add an indicator, and the indicator will change color when we reach the point where the titration is at its end point. And it turns out that indicators actually are weak acids, and they have hydrogen ions that are formed. And so the buffer, they'll do this symbol here, HIN, but the buffer, not the buffer, the indicator is actually there changing its form. So the indicator will exist in two forms, HIN, and then if we add some OH minus to this, the indicator will also react to it, and it will get I minus and H2O. These two species right here, the HIN and the I minus, or the IN minus I should say, those two species, the HIN and the IN minus, are what cause the color change. And so we can see here that, when we have something like methyl violet, when it's yellow, the pH is lower. And that means that there's more H plus ions in solution. That most likely means that the HIN form is where it's yellow, and the IN form, IN minus, is where it is violet. Now this color change starts to take place where you get, this huge change in a ratio between the HIN and the IN minus. Something else that's interesting about indicators that we're going to use is that they, since they're weak acids, they have a pKa. And when you want to pick an indicator that's going to work with your titration, you want to have one where the pKa is equal to the pH at the equivalence point. Now this may not mean much to you now because you're like, what is he talking about with equivalence point? But we're going to come back to this and we'll pick out an indicator that would be good to use. We'll go back to this chart and see. The most common one that people use is phenolphthalein because it has a pretty large range where it changes and it covers most of the titrations that we do. It's also a really startling change, which is nice to see. Okay, so the first type of titrations that we're going to do are strong acid, strong base titrations. These are the ones that you did last year. So when we titrate a strong acid and a strong base, we have something like, HCl and NaOH, and they are combined together and they form H2O and NaCl. This is the typical acid-base yields salt plus water. You've done a titration before with a burette. In this case, they have it containing NaOH. here's our beaker containing HCl and our indicator, phenolphthalein. And they also have a pH meter to monitor the pH. And the reason why they do this is because they're making a graph. And so here's my graph, and you can see when I look at the graph, the pH starts low. It increases, but only at the very end. The pH starts low and stays pretty much flat. And then you get this sudden increase where you get this jump, and you have this neutralization of the acid and the base. And the pH will be right around pH 7. If you keep adding base like they do here, and you get excess OH minus, you can see that the pH rises much higher, and then it levels off top here. So this is a sigmoidal curve. It has this S shape to it. The equivalence point is the point right in the middle of this titration curve from where you are on acid, changing, and you're adding base, and you're perfectly neutralized at that point, that inflection point. Okay, so this is for my strong acid, strong base. And we could do some kind of cool problems with this where we're not at the equivalence point. And I'll do some of those in class with you where we keep adding more base and we can monitor the pH as we go along. Those are kind of cool to do. But what I wanted to really focus on were the ones that are most focused on the AP exam. And that's where you have a weak acid and a strong base. And with those weak acid and strong base titrations, the curve looks different. The curve isn't flat here as we can see in the strong acid, strong base titrations. The curve has quite an increase to it, and eventually it reaches an equivalence point. But notice, the equivalence point is up here. It's above 7. And we need to be able to explain that chemistry and understand why that is the case. Okay, so let's go through and look at this in detail. So our first point that we're usually asked about is point number 1 over here. At this point, no base has been added. And so we have a weak acid. And this is just a regular weak acid problem where you have to use the Ka to find the H plus or the pH. The next situation is one in which we've added some base. When we've added some of the base to the acid, we reach this part over here, and this is our buffer zone. This is the point where we have a buffer that has formed because we have added some base, and there is some of the original acid and some of the conjugate base there. So we have a buffer, and we can use Henderson-Hasselbalch. There's actually a very special point along the titration where we're halfway, and at this point, sometimes they ask you about this, and if you realize that it's the halfway point, you know that the pH of the solution is equal to the pKa of the acid, because the ratio of A minus to HA is 1 to 1. And that will save you some time if you realize that, but you can always work out the math. The third calculation that they ask you about is at the equivalence point, and this is the hardest calculation of the bunch. It's difficult because when you do this, when you're at this equivalence point, you'll only have conjugate base left from the weak acid. So you have to then write a new equation where the base hydrolyzes the water and forms OH minus. And when this happens, you have to use a Kb instead of a Ka and find the pH. So that question is the most involved. So let's look at what a sample question would look like for a titration so that you can see what you'd have to do. So here the problem says that you have 0.8 liters of a 2 molar methanoic acid. It's mixed with 200 milliliters of 4.80 molar NaOH. And when I do this reaction here, notice what I do is I actually have something like an ice table, except I'm using moles because it's not an equilibrium problem. So I change the moles or the molarity of the methanoic acid using the liters to moles. And I change the molarity and milliliters of the base to moles as well. I then see which one I have more of. I have more of the methanoic acid. These are all reacting 1 to 1, so the base will get completely used up. So the base gets used up. it takes some of the acid with it, and it produces some of the conjugate base. I have 0.64 moles of the acid left over, 0.696 moles of the conjugate base left over, and now I can really simply just plug this into my Henderson-Hasselbalch. But you have to realize that you've actually formed a buffer here. And so now my pH is 4 times 4.096. My H3O plus is 8 times 10 to the negative fifth. So this is a situation in which I actually have, something going on where I formed a buffer. Let's try one in which we reach the equivalence point. And so when we reach the equivalence point, then we have a lot of calculations that we really have to do. So we're going to try and do that in class tomorrow. I'd like to, sit and go over that with you in person because that's really challenging. And then we'll review it in the next video as well. All right, thanks so much for watching.